Welcome to the lecture on issues in welding designed for static loading. So, we talked about many aspects in welding. We talked about the metallurgical aspects, we have talked about the cracks, then solidification behavior and all that. Now, towards the end we will have the other aspects also need to be studied and also other issues while we do the welding. So, for the welding metallurgists, they need to know certain aspects, how that what are the design aspects which are taken into consideration or which are to be given due importance while we go for the welding. So, first is that the design for the static loading. So, in most of the cases either you have the static loading, the weld may be subjected to or it may be subjected to the dynamic loading. So, if you talk about the static loading, so here the you are talking about the strength of the material. So, the UTS is basically taken as the strength. So, that is your ultimate tensile strength of the material is taken into consideration, that how long it can sustain. Then what is happening, that in most of the cases you will have the occurrence of or the presence of the stress concentration. So, when you have the stress concentration in the weld and as the load is increasing, then the yield point may be reached soon at the point of stress concentration. So, what happens that when the yield point is reached, there will be small yielding, and then further after slight yielding, this maximum stress will be transferred to another point of the weld. It may be because when you have the somewhat straining, maybe that other point where other stress concentration is achieved, there the stress value will be more than the limit. So, in that case that will be shifted to another point. So, this way this will be continuing until the stress distribution over the whole load carrying section is uniform. Now, this is the such balancing of the stress concentration will be taking place under the static loading cases, and for the purpose of the stress calculations, they are not affecting the final stress values in the weld to much extent. So, basically in this lecture we are going to have the discussion on those considerations which are required for the designing of the weld when the weld is subjected to static type of loading. Now, in that case if you talk about the weld design. So, in these cases we are normally we are designing the weld for the strength and rigidity of the weld. So, if you talk about the all the weld designs. So, if you go to the design for the strength and rigidity, you are going for the design of the strength and rigidity. So, you require in any weld you require the strength as well as the rigidity, and what we feel that we must have the welds in such a way that it will not be failing, it will not be breaking or yielding when subjected to that reasonable loads or reasonable overloads. So, basically you are normally designing for the strength, you are in normal machinery. Similarly, that in a weldment also we are designing for the calculated loading, and then for that you have the design formula for the strength which are used for such applications. So, you may also you also design using these deflections, but in many cases and the criteria is about the deflection, because deflection should not be more than a limiting value. So more than certain value. So in that case deflection under load, that is also one criteria for which you are going to design these welding. So and again, if you talk about the weldments, then in the case of weldment you may have certain part which are having the loads, and in certain part you do not have loads. So that normally happens in a, if you take any member. So but you have to have also taking into consideration the weight of its own weight of the specimen also. So if you look at the material, you will have to have all these considerations into mind when you are designing for the designing that weld for the strength and rigidity. So for that you have first the use of the design formula. So you have the standard design formula is there, and in these formula you will have the different terms will be used. So if you are going for the design formulas, so you will have the standard terms like you have the stress value or the EIZ, and all these you have stress, strain, you have the modulus, all that sectional modulus, and all that terms will be coming up. A moment of inertia term, that will be coming up. So these terms are basically used, and the load load is the force that is stresses a member. So when there is load applied, so that will be creating the stress on the member, and once you have the that, so that will be resulting into strain. So strain you will have so load will be creating the strain, and this strain is measured in many terms, and you may have the strain as elongation, or you may have the contraction, you may have deflection, or you may have the angular twist. So different way you will have the strain which is measured, and every member will be designed according to what type of load and what is the allowable strain which is there in that particular material. So you will have the allowable limits in most of the cases, and you will have the material chosen for that purpose. So that will also depend upon the material which is chosen, and then also the size and shape of the material also which is being chosen. So then the properties of the material which you normally are thinking of, or on which you are focusing will be like you have strength or modulus of elasticity. That is what we have earlier seen also. Then you have radius of gyration. So that also is one of the properties. So that will basically determine the load carrying capability of the material. Now in most of the cases, the design formula which is developed, so normally what we do is we have if you talk about the deflections of in a cantilever type of beams. So in those cases, if you talk about the cantilever beam, in that case, so as we know that if you have a cantilever beam and you are applying a load, so if you are applying the force, in that case you will have the deflection, and that deflection will be FLQ upon 3 EI. So as we see that you will have F is the load which will be bringing into the deflection delta, then L is the length of the cantilever beam. Similarly, E is the modulus of elasticity of the material, and I will be the moment of inertia. So, what we normally design, our basis of design will be that we should have the minimum amount of deflection. So, for that, as we see that we will try to have the material with large and large values of E and I. So, so normally if you talk about the different materials, so among the different materials if you talk about the values of, so E and I should be large to have minimum deflection. Now, if you talk about the having the larger and larger values of E. So, if you talk about the value of E for the steel, so it will be something like 207 10 raised to the power 9 Newton per meter square. So, that is the value of E. Similarly, another is the I, that is your moment of inertia, and that will be depending upon the different type of cross section of the material. So, accordingly, and and also another factor which is going into while consideration is the cost also while you are making the different cross section. So, accordingly you can have these cross section formed by the different forming processes, so that you have a larger value of E and I. So, you can think of having the smaller amount of the deflection. So, that is how you design design formulas are used, and you design for a better loading. So, when we talk about the loading conditions, so if you talk about the loading condition, then there are different types of loads which are applied. You may have the tension, you may have compression, you may have the bending, shear and torsion. So, these are the different types of loads which are applied, and when these loads are applied, then the material comes under the stress, and that stress will cause the movement inside the member, and and how much movement will be there, that we have already discussed, that will be depending upon the value of the modulus of elasticity of the material, and certainly that shape which will be governing the moment of inertia of that particular shape. So, what we do is we normally we have the definition of the working stress or allowable stress, and for that we define a term known as factor of safety. So, you will have a failing stress, and that will be divided by the factor of safety. So, that is safety factor. So, this way you have the the definition of the allowable stress or working stress, which is which is what is set so that you can have the performance of the welded specimen satisfactory in the long run. Then the next point which is important is the material selection properties. So, material properties or the section properties. So, if you that is your material properties. So, if you talk to the material properties or the section properties also. So, under that you will have the different material properties are there. You have the or we will also talk about the section properties, that is, and that is what we have studied, that you have material property that is E, and then section properties will be depending upon that. You will have a moment of inertia or you will have other parameters, other terms will be there which we will be talking about the section properties. So, you will have the commonly we use these modulus of elasticity So, that is one property of the material. Then you have the Poisson's ratio, you have modulus of rigidity, then you have section property, you have a moment of inertia, then you have a polar moment of inertia and section modulus. So, these are the material and section properties which are used for the design process when we are dealing with the welding process. So, we have to discuss about the properties. Now, among them the first property is the modulus of elasticity. Now, what we see, because many a times we we require a high amount of ductility in the structural members, and because that having that property, basically it will be taking up accommodate appreciable amount of strain in the and also it will be redistributing the stresses without the permanent premature fracture. So, that way these properties are desired. Now, if you talk about the stress strain diagram, so these properties are basically defined on the basis of the stress strain diagram. So, as we see, when you typically see the stress strain diagram of one steel, so your the stress strain diagram goes like this, the engineering stress strain diagram, and what you see is that you have a linear portion which is which is there up to this point, and then it becomes non-linear. So, the modulus the modulus of elasticity of the ductile material will be in this region it will be defined. So, it will be ratio of the stress to strain for this region. So, that will be a constant value. So, that way this modulus of elasticity will be defined, and it will be representing the stiffness of the material. So, here it will be fracturing, and you will have the so slope of this region, that is a constant value which is obtained. So, this stress upon strain, that slope will be known as the rigidity value or modulus of elasticity, and normally in tension and compression it is assumed to be same for the material. Then you have the rigidity or stiffness. So, that is the amount of stress of the material that can withstand. So, that is the rigidity of the material. So, then second portion is the second point is the Poisson's ratio. So, as also we know that the Poisson's ratio is the ratio of the lateral to the longitudinal strain, which is happening, because when you are straining the material, in that case you will have the change in length, whereas will be change reduction is, so increasing the length will be, because and there will be strain also in the lateral direction also. So, that will be negative. So, normally you will have the the Poisson's ratio which is defined is minus of lateral strain to longitudinal strain. So, so the negative sign tells that the lateral strain has the negative sign to longitudinal strain, because the mu has to be positive. So, in that case this is your Poisson's ratio, and mostly the Poisson's ratio will be varying between 0.25 to 0.35. So, but for the rubber it is approaching close to 0.45. So, in that case that can be correlated about the elastic properties of the material. Similarly, you have the modulus of rigidity also, and that is known as the bulk modulus of rigidity, that property is there. So, when you use the tangential or shear stress, in those cases you will have the ratio of stress to strain that is defined as the modulus of rigidity. So, that is defined by the term G. So, if you try to see the correlation between this G and the elastic modulus of elasticity. So, there are also correlations like you have G as E upon 2 into 1 plus mu. So, this way you will have these these terminologies which needs to be understood in such cases. Then coming to another term which is important in these cases is the moment of inertia. So, it is also known as the second moment of inertia, and it is basically denoted by I. So, it will be expressing. So, it expresses sum of products by multiplying each element of the area by square of its distance from a given axis. So, this way you basically find the moment of inertia, and this axis will be lying in the plane of the cross section. So, you will have one axis, and about that you will be having this value of the moment of inertia, and normally you will have the unit, that is area of so you will be multiplying the each element with the square of the distance. So, you will have the unit that is in mm4. So, what we do is that normally it will be talking about its tendency towards the rotation, I mean about the axis, and this is a measure of the resistance to that rotation. So, offered by the geometry and the size of that section. So, it is basically a very useful property of the material in solving the design problems when there is involvement of the bending moment. So, normally it will be used while solving the rigidity problems, and there are different methods for finding these moment of inertia of the structure, and normally what we do is that if you talk about the any rectangular section with different axis of reference. So, you will have, although you have different methods of finding these moment of inertia. So, what we do is, if suppose you have this is the B and this is D, and if you are talking about this axis. So, you will have in that case, if you so this is your axis of so this is your basically neutral axis, and this becomes the axis of reference. So, you will have the finding the moment of inertia if you try to have it about the neutral axis. So, about neutral axis it will be In, and in that will be B into d cube upon 12. Similarly, if you take the moment of inertia of the same rectangle about its baseline. So, if you try to find about its baseline, it will be B d cube by 3. So, basically the knowledge about the moment of inertia will also be used in finding the the value of the polar moment of inertia, that is your J. So, that is used for finding the polar moment of inertia. That is J. So, this J is also found out about the axis which is right angles to each other, and also the section modulus. So, that also has a role in solving the problem for the design that is related to the rigidity. So, in case of rigidity design problems, these terms are also required. So, if you come to know something about the polar moment of inertia, so the polar moment of inertia, that is J, it is it is basically the sum of any two moment of inertia about axes at right angles to each other. So, you will have the polar amount of inertia which is taken about an axis which is perpendicular to the plane of the other two axes. So, in that case J will be Ix plus Iy. So, that way you find these polar moment of inertia. Then other parameter which is there, which is found to be useful while we talk about the designing that load or weld under the static loading. So, that is your that terminology is the torsional resistance. So, it will be normally replacing that less accurate polar amount of inertia, and normally torsional resistance you will have as W T cube upon 3. So, R is normally the torsional resistance, W is the width of the flat section, and T is the thickness of the flat section. So, so normally when you have the torsional type of loads are involved. So, in those cases for the flat section we normally use this formula, the R equal to W T cube upon 3, and once you have the R found out. So, once you find the R, then angular twist can be also found out. So, angular twist will be TL upon ES into R. So, your ES is the modulus of elasticity in shear. Similarly, you will have the L is anyway the length, and then you have L is the length of flat section. Then you have so other terminologies are known. T is the torque, so that is what we have we know, and then R, as we know, R is the torsional resistance. So, this is basically these formulas are used for finding these angular twist in the flat member. Then also as we discussed, you have another parameter which is important is the sectional modulus. So, section modulus basically will be the ratio of it is ratio of moment of inertia with respect to neutral axis and divided by distance, that is C from neutral axis to outermost fiber of the section. So, basically it will be ratio. So, if you talk about the Z, that is your section modulus, that will be I upon C. So, you know, it is the measure of the strength of the beam in bending. So, there we normally use these section modulus. Then apart from that you will have other terminologies like radius of gyration. So, that is also the distance of the you know, neutral axis to the imaginary point, you know, where the where whole you know at that point it is assumed that the whole area of the section is assumed to be concentrated, you know, having the same moment of inertia. So, in that way you find the r, and that radius of gyration is normally under root I upon a. So, that is you know, so that is dividing by the area, you will find the radius of gyration. So, normally when you talk about the you know, welding design features, what we have normally to do in the case of you know, welding is that you will have to know the shape, you know, in order to decide upon the size, shape, and the you know and the type of weld. So, to know, you need to have the you know, ultimate and permissible safe stresses, you need to have the load to be transmitted to the weld pool. So, these are, you know, these things are required. So, once you know that, then you can have the you know, depending upon the these values, you can have the calculation of the stress from the weld, all that can be done. Thank you very much.